Welcome to today's Explainer. We're going to go ahead and map out an atmospheric flight plan, setting the stage to really demystify those invisible forces. Temperature, humidity, wind, the things that absolutely dictate our weather and ultimately our safety up in the skies. So here are the 4 waypoints we're hitting today. First up, temperature, humidity, and saturation. Then, lapse rates and stability. Third, the forces driving our winds. And finally, local wind systems explained. We're pretty much moving from the micro level of a single air parcel all the way out to the macro level of global wind forces. Let's get into it.
Section 1. Temperature, humidity, and saturation.
Okay, to grasp the baseline rules of atmospheric thermodynamics, we really need to nail down the definitions that matter most. For aspiring pilots or just, huge weather geeks, these are literally the invisible gears turning behind every single forecast you'll ever read. So, dew point. That's the exact temperature where water vapor condenses into liquid water. And relative humidity? That's just the measure of saturation, where 100% means the air is maximally saturated. Now, the absolute magic rule to remember here is the spread. When the spread between the actual air temperature and the dew point gets within 2 degrees Celsius, or about 4 degrees Fahrenheit, we are rapidly approaching full saturation.
Which brings up an inevitable scenario. What happens when the temperature perfectly meets the dew point? Okay, let's dive into this. When these two values match up exactly, relative humidity hits that 100% mark. At that point, the water vapor simply has nowhere left to go. It absolutely has to condense, transforming from this invisible gas into tiny, suspended liquid droplets. And that's exactly what gives us visible fog.
Let's see how this builds into a very specific and honestly, super common threat: radiation fog. This strikes when 3 specific conditions align. First, you need clear skies for maximum radiational cooling of the ground at night. Second, light winds, ideally under 5 knots. That keeps the fog shallow but stops it from just blowing away completely. And third, a moist, shallow air mass sitting right near the surface. Oh, and if you're in a valley or a low spot, the cold air drainage off the surrounding slopes makes this cooling way more intense. It creates this incredibly thick mountain valley fog that is just an absolute nightmare for VFR departures.
All right, Section 2, lapse rates and stability. We're talking vertical movement.
Now we're transitioning from raw surface thermodynamics into vertical movement. Basically, we need to understand exactly how temperature behaves as we climb, because that completely dictates the stability of the atmosphere itself. We're comparing 2 really crucial rates of cooling for rising air here: the dry adiabatic lapse rate versus the saturated adiabatic lapse rate. The key is in the difference between them. Unsaturated or dry air cools much faster as it rises compared to saturated air. But why? Well, because when air is saturated and condensation happens, it releases latent heat, and that release of heat actually offsets the cooling process. So saturated air cools at a slower rate as it gains altitude.
Look really closely at this specific number, 3.0 degrees Celsius per 1,000 feet. This is the exact mathematical value for the dry adiabatic lapse rate. Literally, if you're preparing for aviation exams, burn this number into your memory right now. It is a vital, completely non-negotiable metric for calculating cloud bases and for understanding precisely how an unsaturated air parcel is going to behave the second it's forced upward. And this brilliantly illustrates how these lapse rates actually dictate real-world flight conditions. So when the environmental lapse rate, which is just the actual measured temperature of the surrounding air, is less than the saturated rate, we have absolute stability. The air totally resists moving up, which traps haze and gives you really smooth, but unfortunately poor visibility flying. Now, if the environmental rate is greater than the dry rate, bam, we get absolute instability. Air just accelerates upward independently, triggering some nasty convective turbulence and showery precipitation. Finally, conditional instability. This basically means the air is completely stable if it's dry, but highly unstable if it becomes saturated and gets forced upward by something like a mountain or a weather front.
Moving on to Section 3, forces driving our winds, focusing on horizontal movement.
We're shifting gears now from vertical instability into the fluid dynamics of horizontal movement. Honestly, it helps to think of the entire atmosphere as just this giant, continuous engine. There are 3 invisible hands that basically govern all airflow. First up is the pressure gradient force, or PGF. This is the primary ignition of our engine. It's the fundamental force moving air directly from high pressure to low pressure. But as you probably know, wind doesn't just flow in a perfectly straight line. And that's thanks to our second force, the Coriolis force. Finally, right near the Earth's surface, we have friction, which acts as a major drag on the whole shebang.
Let's break down that second force for a second, the Coriolis effect.
Because the Earth is constantly rotating, moving air gets deflected. It's just physics. In the northern hemisphere, winds deflect to the right. In the southern hemisphere, they deflect to the left. It's actually fascinating to note that this rotational deflection is exactly zero right at the equator, but its magnitude increases proportionally as the wind speed gets faster.
Now, what's really interesting here is how we can visually ground the physics we've been talking about. Take a look at this example of cold advection over the Gulf of Mexico. When strong, cold, high-pressure winds, driven by that pressure gradient we just talked about and steered by Coriolis, flow south over these relatively warmer waters, the cold air quickly becomes saturated from the evaporating moisture down below. This clash is incredible. It creates this dense steam fog, which can literally drop visibility to absolute zero, even when the winds are howling. But what happens when we get really close to the ground? Well, we enter the friction layer. This generally extends from the surface up to about 2,000 feet above ground level. Surface friction physically slows the wind down, and because the wind is slower, the Coriolis deflection is also reduced. This imbalance is super important and means surface winds no longer blow perfectly parallel to the pressure isobars. Instead, friction causes them to angle across the isobars, pointing directly toward lower pressure.
All right, final stretch. Section 4, Local Wind Systems Explained, focusing on geography and airflow.
Let's bring all these grand thermodynamic and fluid dynamics concepts back down to Earth for a minute and see exactly how local geography literally sculpts the wind. We've got anabatic winds, which are daytime upslope flows caused by the sun heating up mountain slopes. Then we have katabatic winds. These are the nighttime downslope flows triggered by radiational cooling, where dense, cold air just sinks right into the valleys. And then there's the bora, which is the severe cold gravity wind spilling over plateaus. So the crucial point here is the specific aviation hazards these create. Katabatic and bora winds in particular can generate sudden, incredibly violent downslope wind shear right on your approach paths. You definitely want to watch out for those. Finally, we have your classic coastal systems. The sea breeze is a daytime onshore flow. Rapid daytime heating of the land creates a localized low pressure, which basically just pulls the cooler, denser ocean air straight inland. But at night, the land breeze takes over. The land undergoes radiational cooling way faster than the water does, completely reversing the temperature and pressure gradient and sending the wind blowing right back offshore.
So, what does this all mean? Well, it leaves us with one final, pretty important question to consider. How will mastering these invisible atmospheric forces change the way you navigate the skies? Honestly, predicting this massive weather engine, from the exact moment a dew point spread triggers a wall of fog, to understanding exactly how a valley funnels a dangerous katabatic wind, it isn't just an academic exercise. It is the absolute ultimate key to aviation safety and true mastery of flight. Thank you so much for joining me on this explainer. I hope you took a lot away from it.